Welcome everybody to the webinar Flash Memory in Embedded Linux Systems presented by Toradex. Before starting, please pay attention to the following notes. This webinar will be recorded and available within a week in the Toradex website, www.toradex.com/webinars. Throughout the presentation, you are able to ask questions using the webinar tool. I won't answer them right away, but in the end, we will host a Q&A session. If even then you don't have your questions answered, I will email you afterwards. Interactive polls will be run throughout the webinar, where you will be able to answer multiple choice questions. My name is Leonardo Veiga, and I am an FAE from Toradex Brazil. I'm engaged in an innovation project related to flash lifespan estimation, and therefore this webinar is a result of this work in progress. And before starting, the agenda will be as follows. We'll begin with a very short introduction to the Toradex company, and it will already be addressed in the context of flash memory. In what regards the flash technology itself, you will be provided with a high-level overview of many key concepts that are base for any flash usage, and thus prerequisites for understanding how Linux deals with it. Then we will understand the big picture of how does Linux handles flash storage. From then on, aspects of health and lifespan estimation will be discussed, and we will end the presentation talking about the Toradex Flash Analytics tool, which is being developed under the Toradex Labs brand and aims to deliver added value for Toradex customers. Toradex is a company that develops and sells highly reliable ARM-based system-on-modules. We focus in reliability, long-term maintenance, and scalability when it comes to the hardware. And this is all based in our offerings that are composed of two computer-on-module families, where all modules within a family are pin compatible. But we deliver more than just the hardware itself. Toradex has in-house BSP development, therefore we provide production-ready Windows CE and Yocto-based Linux, which are maintained over the product lifecycle. Since one of our pillars is customer focus, we deliver an experience focused in ease of use, providing a premium quality support and a wide development ecosystem. Toradex has a direct sales model, meaning we don't sell through distributors, therefore we have a global presence and a close contact to our customers. Local offices across the globe enable us to provide high quality local support and local stock, which gives you competitive advantage if your product also has a worldwide presence. Now that you have an overview of Toradex, let's also be introduced to flash memory. As it is a broad term, the word flash refers to non-volatile storage technologies, which, different from hard disk drives, is based in semiconductors and don't have mechanical parts and therefore present a variety of benefits, such as high capacity in a small enclosure, low power consumption, and mechanical shock resistance, among others. Examples commonly found in our day-by-day lives are pen drives, SD cards, SSDs, and even embedded flash memory in smartphones and tablets. And this slide illustrates the intersection where both Toradex and Flash NAND have a common presence, which is the embedded systems market. Notice that the use cases presented require highly reliable, cost-effective solutions. In addition, those markets are competitive and they demand that you release products with a fast time to market. And Toradex can help you with all those topics. When it comes to flash memory, there are mainly two base technologies behind it, which are NAND and NOR. They are named after their respective architectures at a transistor level. We will focus in the NAND technology in this webinar, since it is found in our system on modules, whereas NOR is usually used in critically reliable applications, since it is more expensive and has lower storage density per square inch. Even though NAND costs less and is provided in many options of high storage capacity ICs, the software stack to support its use is much more complex due to its operation. Let's relate our hardware to NAND technologies. Our offerings are composed of two computer module families, Apalis and Colibri. Apalis focuses high-speed interfaces and the most powerful computing capabilities, and Colibri is the best choice for industrial connectivity and low-end devices. There are some modules in the Colibri family that are equipped with raw NAND chips, such as the Colibri IMX6 ULL, Colibri VF61 and VF50, and some of the Colibri IMX7 configurations, while the other modules are equipped with eMMC, that is managed NAND. Keep these terms in mind, these words in mind. We will talk about them as the presentation goes on. And to begin with, let's have a look at a generic NAND die with a high level of abstraction. It has three distinct divisions: blocks, which are presented in blue, pages in red, and cells in orange. The names are conveniently related to the NAND operation as well as construction. A cell is the smallest representation and is the structure that relates to the bit level storage. A page is the smallest array of cells that can be accessed in a single operation, a read or a program, and its size is usually in the range of 4 kilobytes. A block is the smallest array of pages that can be erased. It is usually made from 32 to 128 pages, but may vary, and it is in the order of half a megabyte or greater. And from now on, we will present the concepts that relate to those terms and start by the NAND cell. In summary, there are mainly two technologies behind NAND flash, and they are SLC and MLC. And they are transistor level technologies. SLC stands to single level cell, and 1 bit is stored per cell, and the voltage between a 0 and 1 is very distinct, providing a good reliability as well as endurance. Whereas MLC, illustrated in the right-hand side of the slide, stands for multi-level cell, and it can store 2 bits in a single cell. As the density of data increases, the reliability and lifespan of the NAND flash decreases. All Toradex modules are equipped with those. The raw NAND-based devices have SLC, and the eMMC-based devices have MLC. I have put here two other technologies, which are TLC and QLC, and they are used in consumer electronics, and they store respectively 3 and 4 bits per cell. Those are rarely suitable for embedded systems. It is also important to say that even for SLC, the trace width, that is the size of the cells in nanometers, also influences the endurance of the flash. And this is a point where I would like to run the first poll and understand how long your device will be in the field. I'll just leave approximately 15 seconds for people to answer, and we will see the results right after. Good. Most people will have devices in the field for 5 to 10 years. Thank you. And that's a long time, so we have to be concerned about the flash technologies. Still on the NAND cell topic, some manufacturers provide NAND-based MLC devices that can operate in modes similar to SLC and bring a few advantages to MLC. On the right-hand side, we have the fast mode, and it is in fact the same design as MLC and makes the read-write performance faster at the trade-off of using half the die capacity. Whereas pseudo SLC at the left-hand side, also known as enhanced user mode, is a modified MLC that, at the trade-off of using half the storage capacity, enhances the lifespan, speed, and reliability of the device, getting closer to a purely SLC. And here we have an illustration that summarizes the differences and the most important points to guide you when choosing a technology. The arrows summarize the overall density, cost, reliability, and lifespan trends according to the technology, whereas where the color gradients point towards better, which is represented by the blue color, and the orientation points towards higher or bigger at the tip of the arrows. We have modules that support pseudo SLC, such as, for instance, the IMX6-based modules. But now let's focus on the practical aspects of NAND operation. Basically, NAND memory does not operate in the traditional way we are used to with HDDs and RAM memory. Instead of read-write operations at specific bytes, we have the following. Read operations must be done in pages, as well as program operations. A bit can only be switched from 1 to 0 without the need to erase it, and therefore a write operation may consist of several NAND operations. Erase can only be done in blocks, and therefore it is slower. It can be part of a write operation, and therefore ideally it is good to erase unused blocks ahead of time. In addition, bits may get flipped from 1 to 0, and not only randomness influences it, but also environmental parameters such as temperature. In addition, as a block wears out, bit flips happen more often. This is why we need software to monitor and correct those, which is named ECC, or error correction code. It does not work forever though, mainly due to wear. When it is impractical to keep recovering data from a block, which is defined in software by an error threshold, the block is marked as bad and not used anymore. The average number of erase cycles before a block goes bad depends on the technology, having SLC the greatest endurance, and on the geometry of the NAND traces in nanometer, being higher values better since bigger silicon cells last longer. To prevent the flash from being worn out too soon, wear leveling algorithms are implemented in software. The basic idea behind it is to always write data to the block that has the lowest usage, that is, the lowest number of erase cycles. And for that purpose, a controller maps logical addresses seen by the application to physical blocks that are transparently and constantly updated. In the example illustration, the logical block in red is mapped to different physical blocks at different points in time. There are two main concepts behind wear leveling algorithms. The dynamic wear leveling does not move static data around. In other words, static data physical blocks are never erased, and thus a percentage of the NAND will not be used to its full extent. And this percentage is use case specific. And the static wear leveling, on the other hand, it moves data around, thus all NAND blocks contribute to increased lifespan of the device at the trade-off of a more complex logic and a performance penalty due to the need for additional read, program, and erase cycles. It is very important to always leave free space for the wear leveling to work well. because it needs to move data around. Also, leaving small amount of space greatly impairs performance due to the need of executing more erase operations synchronously. If you remember, erase operations happen in blocks, and blocks are big, so those operations are slow. And also, there is a concept of the garbage collector, which during the operating system idle time erases the dirty blocks, so you can have as many ready to program blocks available at a point in time. Now that we saw the challenges of the software side of using the NAND technology, I would like to introduce to you the concept of managed NAND. It is basically a raw NAND with an integrated controller that abstracts the software challenges and provides added value features, such as reliable write, different write protection modes, and standard comments. There is an intersection between raw and managed NAND offerings by manufacturers in what regards to storage capacity, but usually you will find the following differences. Raw is SoC, whereas managed NAND is MLC, and when industrial grade, it has pseudo SoC mode. And therefore, managed has generally greater total storage capacity at a lower cost per bit. And one of the de facto standards for managed NAND is the eMMC, which stands for Embedded Multimedia Card and complies to the JEDEC MMC standard. And the diagram you see on screen illustrates a high level of abstraction, a practical difference between raw NAND and eMMC. And this is the last slide dedicated specifically to flash technology. And from now onwards, we will begin an overview of how does it work with Linux. So let's start a poll before we proceed and understand if you have worked with flash memory before. Maybe you did hardware design or used it with microcontrollers or even on other embedded Linux systems. Okay, and as a result, I can see that some of you have already used NAND in hardware designs or microcontrollers. Therefore, you probably had a good deal of knowledge of the presentation so far, and probably you know the difficulties of making things work properly. Well, this is the first slide where we will understand how does Linux do its job when it comes to flash memory. At a very high level, usually what happens during application development is that you write a user space code which does file operations. How the operations are done can vary depending on the library and language you're using. But at some point, there will be a transition from user space to kernel space. This is the point when the library's functions will make system calls to the kernel. You can make a system call yourself at the trade-off of abstraction and being more prone to error than a well-tested and mature library, such as the C standard library, among others. The Linux kernel then deals with that I/O through what is usually referred to as I/O stack or storage stack, and at its last step, it sends data to the device through a low-level device driver. Due to the differences between raw NAND and eMMC, both have largely different I/O stacks, respectively, the block and the MTD stacks. I would like to highlight that our regular consumers need not concern about implementation details, since this is all taken care of by our BSP team. The block I/O subsystem is the one that handles operations for all block devices, such as hard disk drives and SSDs, and this is where eMMC devices fit. If we have a closer look at the block I/O subsystem, which is conveniently well abstracted in this illustration, we can go through the kernel stack from top to bottom. The virtual file system is an abstraction layer for the user space API. The file system itself implements specific structure to define the concepts related to files, as well as the operations that need to be taken care of, and among other aspects. The generic block layer, which usually includes the I/O scheduler in the literature, is the place in stack that handles all block I/Os and thus abstracts the block devices for the file system, among other aspects. The I/O scheduler takes the queue of I/O requests and sends them to the block device driver according to a specific algorithm. It tries to maximize block I/O performance, and the choice of the scheduler may affect latency, throughput, and usage of the flash. The MTD subsystem is the one that handles operations for memory technology devices, including raw NAND. We still have the virtual file system, but starting from the specific file system, things change. And in fact, even VFS tuning can be a bit different. For instance, since its read-ahead is in fact bad for raw flash devices. And the first thing to notice is that there are file systems specific for raw NAND. They are the ones that implement the wear leveling and garbage collection. Here we can cite UBFS and YAFS2, which are the most popular, and UBFS is the one chosen to be used in Toradex BSPs. The MTD layer is an abstraction layer to provide easy integration between different device drivers and file systems. There is some support for using block file systems with raw NAND, with the addition of an FTL, or flash translation layer, on top of MTD. This is not recommended though, since the implementation of such is not very good for handling the peculiarities of raw NAND. I would like to bring to your attention that an FTL is what actually the eMMC implements, though the flash manufacturers have nice implementations that work very well. In between a flash file system and the MTD layer, there is the possibility to use UB, which is not the same as UBFS and not an FTL. It is a mechanism that maps physical erase blocks to logical erase blocks and provides wear leveling and other features, thus making the life of the flash file system easier. But the flash file system still needs to be aware of how NAND, raw NAND operates. Caching is a mechanism designed to make data available in order to prevent access to slower source of data. Even flash memory, which is much faster than rotating storage, is still slow when compared to fast CPU speeds, and therefore caching is something beneficial for the overall system performance. It may also help to increase lifespan of devices. The Linux kernel implements a cache named page cache that stands between the VFS and the file system and is its most popular cache system. It makes data readily available to the user space applications without it going to the file system. Deeper into the I/O stack, caching effects may happen due to I/O merges to optimize the use of the storage hardware and I/O queues that usually target throughput. As an example of merging I/O, there is the write-back mechanism that keeps data until absolutely necessary and thus prevents data fragmentation and the use of fractions of pages or blocks. These mechanisms, they also make it hard to trace how much of a specific process write is actually hitting the flash. From user space, there is only one way to make sure that your data is being written to disk as you go, and it is by syncing. It is possible to sync data on a file basis, therefore you don't impair performance by syncing the whole buffers. And while syncing makes your application data more reliable to unexpected power cuts, you should think what pieces of data are really important, especially if you write a lot to disk, otherwise it may unnecessarily decrease the flash lifespan. One way to make sure specific files don't get corrupted or unexpected power cut corrupts the system is by doing atomic file updates. Since we already started talking about this topic, let's see it in more detail. Unexpected power cuts may affect the system in a way that it becomes corrupted. This is why selecting power cut tolerant and well-tested components for the I/O stack is paramount for increased reliability. And at the NAND level, having mechanisms to first write data to an unused block and only after that point metadata to it and mark the old block as dirty are recommended. Such a mechanism is named copy on write. This also must be taken into consideration with static ware leveling and garbage collection. At the file system level, journaling file system must be chosen. Basically, it tracks I/O intention and only marks it as successful after changes actually hit the disk or the flash in this case. Metadata or full data can be tracked at the trade-off of performance. And at some cases, and now we are in the low right block of the slide, if reliability is critically paramount, redundancy may be considered. There are different levels of redundancy, which includes having a read-write partition mirrored from a read-only, having recovery partitions, and so on. You may, for instance, choose to start a bootloader at a place that is not affected by ware leveling and does never move the RAM. In the Toradex BSP, you only need to do additional work if you want or need redundancy. Otherwise, our BSP engineering team focuses in providing a power cut tolerant solution. This slide was mainly based on my wanderings through the UBFS documentation, and this is why the first topic listed here is read file system documentation. It is because there you will find a lot of useful information. As a few examples of what can be fine-tuned to improve performance of the system or a greater lifespan, we have some items. Read ahead is a mechanism that the VFS uses to read data that was not requested ahead of time. For instance, when you have a big file of consecutive blocks, such as a video. This is generally good for block devices, especially hard disk drives, but if used together with UBFS, would in fact only provide a performance penalty. Compression, on the other hand, is a good means to increase the flash lifespan, since usually real-world data compresses well. Turning the right timeout for page cache sync may be interesting for some applications, but have to be well evaluated. And free space is almost mandatory if a good ware leveling is to be done. Some people say you must have at least 10% free space, others say 20%. In the end, if you move large amount of data around, more space is beneficial. And now that we saw the NAND flash basics and how does it work with Linux, we will talk about flash lifespan. There are certain aspects of NAND that are measurable, being then the block erase count, which is the number of erase operations issued to each block, and the bad block count, which is the actual number of bad blocks. Usually, each block of the NAND has a spare area with a reserved position to mark blocks as bad, but the ware leveling accounting has to be taken care of from the software stack. To give you an example, in the MTD stack that we saw previously, The UV layer has an erase counter header, and the MTD layer has a bed block table. When it comes to the eMMC standard, it provides out of the box a device health report that gives the device lifespan in percentages multiple of 10%. There is also a set of registers reserved in the standard for vendor-specific health information, which may consist, for instance, of the raw NAND parameters that would otherwise not be available. Notice that the standard is defined by JEDEC, and the health status is only available in eMMC 5.0 onwards. If you know well the right behavior of your application and you are able to estimate how much data you write to flash over time, you can have a rough estimation of the lifespan by multiplying the full device capacity times number of erases and dividing it by the write rate. As we have seen in previous slides, due to NAND operation, if blocks are partially written, suboptimal utilization will lead to a faster end of life. In addition, even though Linux layers optimize well at this point, it may be hard to estimate a global write rate in the beginning of the project, because you usually end up adding things, a database here, another feature there, and then your initial estimation is up. And thus, being able to measure NAND health status and application or global write behavior makes it possible to predict the lifespan of the NAND through modeling. At this step, one of the most difficult tasks may be to measure write operations to the flash due to the complexity of the kernel stack and wide availability of different tools. Validating the proposed model is an important step that must be carried on, when long-term runs and stress tests may help. And then we have the product development, and during that phase, benchmark tests are helpful not only to get the NAND lifespan for a specific product, but also to help optimize the application usage of the flash. At this point, it is expected that the models are validated and you get a reliable lifespan estimation. In field, you may choose to keep running lifespan prediction models to further increase their accuracy, or maybe only monitor the flash lifespan. Setting up alarms to tell when the flash is close to wearing out helps on predictive maintenance. And finally, with the build knowledge, it is easier to start it over for a new project, and you will not only have better estimation from the beginning, as well as do things much faster. Now, we know what we need to see, which is basically the flash health and the write behavior of the system. For that, there is a wide number of tools available in the Linux ecosystem. As example of tools to aid on raw NAND health monitoring, we have the MTD utils and the UV utils, and for eMMC, there is MMC utils as well as any vendor-specific tools. For instance, Micron has a tool named eMMC Parm that provides the vendor health status that this vendor-specific gives us. When it comes to the monitoring of writes, there are tools for observing different places in the I/O stack, and the choice must be done to reflect what data is actually hitting the flash after all the caches and buffers seen previously. And some tools you may be interested are I/O top as well as block trace. You can see in this illustration many tools to observing the Linux performance, and a few of them are suitable for our tests. I have focused more on eMMC during my study, but even if not available yet, there are tools that allow to even add dynamic trace points in the kernel, which would make it possible to track I/O inside the raw NAND stack. And now is a good time to understand how important to you it is to know a lifespan. And we'll run a third poll here. Maybe you only need the health monitoring, maybe you only need the lifespan prediction, or both. Okay, and as we can see, some people need only the health monitoring and others are interested in both, or monitoring the device in field. Thank you very much. And to wrap up this slide, I would like to ponder that actually doing the flash analysis by yourself can be an overwhelming task because it's very time consuming until you have done it properly, at least for the first time. Often people will stop at the rough initial estimation and just replace products as the flash wears out. And this complexity was one of the main motivators of a Toradex project named Flash Analytics Tool. The Flash Analytics Tool is essentially an application focused in providing to you an easy way to monitor and predict the lifespan of NAND flash in the context of your project, which spares you from having to go through the time-consuming process of doing such things by yourself. It is focused in being easy to use by providing an out-of-the-box experience, which is achieved by having the tool containerized and thus available from a single command. It focuses both in monitoring and lifespan prediction of the flash, which saves you from a time-consuming task. A modular approach is being implemented, therefore you can only use what you need and save system resources. Therefore, those of you who answered that you only need the health status could select just that part of the tool. The project conception is to make it usable not only during development, but also in production. And the initial version of the Flash Analytics tool targets only eMMC devices version 5.0 or later. And it means that our latest versions of Colibri and Apali's IMX6, as well as Colibri IMX7 eMMC are supported. Its core functionality exposes interfaces through a JSON API, and a remote user interface is provided for an out-of-the-box experience. This tool is at a very early development state. Therefore, it is not recommended that you trust it blindly and do not use it yet in production. And this is why feedback is very welcome. The preliminary lifespan prediction model uses linear regression, although there is wide room for improvement there in the future. And as people get interested in such project and improvement requests come over, it can have other features added, such as better lifespan prediction models, production-ready releases, and support for raw NAND devices, as few examples of what can be done. And in the next slides, I will explain the context where the Flash Analytics tool is inserted. As Toradex strives towards reliable innovation, we have recently released the Toradex Labs brand a few months ago. Its main focus is to get our customers close to our newest projects, leading to results that deliver solutions for the problems of tomorrow. It is basically a glimpse of our engineering where you can provide your point of view, so we deliver solutions that are well suited for our customers. For more information, I invite you to visit labs.toradex.com, and I will also go through the website briefly at the end of the webinar. And one of the first projects of Toradex Labs is the Flash Analytics tool. Therefore, the context of the tool is the Toradex Labs. And before presenting the tool for you, I have to first talk about Horizon, which is another project that was created inside Toradex Labs. And it is a new software offering by Toradex that consists basically of a minimal Linux distribution that focuses delivering an easy of use, out-of-the-box experience, having over-the-air updates and a container runtime ready to use. In a few words, it is able to run containers, making it easy for application developers to focus on their core knowledge and bring projects faster to the market. To learn more, I also invite you to visit labs.toradex.com/projects/Horizon. And the Flash Analytics tool is packaged as a container image ready to run on top of Horizon. And to end the presentation, I would like to give you an overview of the Flash Analytics tool through a quick live demonstration. A Colibri IMX6 module is set up with Horizon, and the Flash Analytics container image is already installed. We'll briefly go through the Horizon and Flash Analytics 2 project pages, and then bring up the container and browse the remote UI to present the current features of the tool. So allow me a few seconds to switch to my browser. There we are at labs.toradex.com, where you can understand more about it and also browse our projects. And let's see more about the Flash Analytics tool here. You have an overview of the project. You understand its state, which is currently alpha. You understand more about its features, the supported products, and also a project README, which is the first steps to take when trying to use the tool or the project. And here we have a getting started for the Flash Analytics tool, where the first step is to install Horizon. And then there is also a page for the Horizon project. Back to the getting started section. You only need to run two commands. You need to create a Docker volume to store persistent data, for instance, during development phase, and then you start a container for the system-wide analysis. I already have a volume created here in my module. Okay, and so let's list it. Here it is, flash data. And now we can start the container. And let's start the latest development version of it. And check that it is running. Here we go, it was created a few seconds ago, and it's up. And as a last step, in order to access the UI, we have to get the IP from the board. And here it is, 10.22.1.113. And here it is. We have the dashboard, which has the JEDEC standard health status of the device. We have an end-of-life estimation, which is not available since, if you may remember, it is based in linear regression, and we don't have enough data points yet. And we can see the right statistics. And we have a few options here to select from, different configurations. We have detailed health status of flash. So besides the generic indicator, we can also see how many bad blocks we have, how many blocks are configured as pseudo SLC or as MLC, and we can see information block by block, how many raises have been issued to each block. We also have a page for system information. So here's the Calibri IMX6, and we know the kernel version, which is close to mainline here, since the Ryzen will support mainline kernel. And we have the technical information about this specific product, as well as a few settings. Now back to the presentation. I would like to start the Q&A session. Please allow me a few seconds. I'll mute the microphone here and browse the questions in order to select the first. Okay, first one is, what does VF50 has, managed or raw flash? VF50 has a raw flash NAND, which is based on SLC and has 128 megabytes. Here is a question that is very complex. Some time ago, I needed to port Linux to a board that used a raw NAND. At the time, 2012, we chose JFFS2 because the UEFS had a serious flaw, which was basically not to make sure the sectors were erased, respecting block erase times. Can you tell me if this problem has been solved? What if there are other acquaintances? And for my application, power cut, hardware reset is a reality and we need to deal with it, not being able to guarantee that situations like this with regard to the time of sector deletion will be guaranteed. To know the very specifics you're talking about, I need to consult with the BSP team, and therefore I ask that I reply to you by email. But what I can assure you is that power cut tolerance is being tested and is a topic that we take very seriously when we do the BSP support for our specific computer modules. Okay, here's a question. It asks if the Flash Analytics tool will be supported in Calibri T30. Basically, the T30 has eMMC with 5.0 JEDEC standard. Therefore, it would be supported by the tool in theory, but Toradex does not support this computer module yet. Endurance is measured in number of write cycles, or it also depends on being powered for a certain number of years. Basically, endurance depends on the number of erase cycles. The more you erase a block, the more you wear that block out. And what basically happened is that you read voltage levels from the NAND cells, and as they are worn out, these voltage levels, they drift and they become wider, okay? And therefore, at some point in time, it will be impractical to read the correct voltage level in order to know the bit status. Okay, here's a question. Is it possible to get the sources of flash analytics tools? This is being internally discussed right now because Toradex Labs is a very new project, and therefore keep an eye at labs.toradex.com, and we will make it clearer in the near future. Is it possible to run the tool on older modules like T30? Well, T30 has eMMC, and the T30 eMMC complies to 5.0 standard from GDEC, so it has the help report, at least for the newest version. And so far, Horizon is not supported on the on T30, and this is the main restriction. Are there any limitations to the NAND MTD I/O? Well, basically, it is open source, so you can see how it's implemented and make changes if it comes to that. And you can choose which file system to use. So you can have, for instance, YAFS2 or UB and UBFS. One limitation is that currently there isn't a FTL that is very well implemented, so you cannot use a block file system without having many drawbacks. And that's what I can think of right now. Maybe I can best elaborate on that later. Okay, there is another question. You said the tool is not production ready yet. Will it be available for production ready, and when? Well, basically, Toradex Labs is a project where we will work closely with our customers. So the more requests we have, the more aware we get that this is really important for you, and we can best improve on top of that. And that's it. I would like to, before finishing, just say that along with the recording, this presentation will be available, and you can see more research references and useful links. Thank you very much for your interest, and have a nice day.